Welcome guys. So this video basically is we will talk about the harmonic oscillator. So this is because in the quantum mechanics that I have already encountered the harmonic oscillator for various times, and I don't want to do it again. So I want to summarize all of it in this video. Okay, so that's starting. So our Hamiltonian will be p squared divided by 2m, and this is our potential terms. Okay, so that's this omega is also k over m. Okay, square root of k over m. Okay, so first the Hamiltonian motion, Hamiltonian motion. Let's quickly summarize. So partial h partial p will be p divided by n, and the partial h partial x will be m omega squared x. So Hamiltonian equation will be this is x dot, and then this is the negative p dot. So right. Okay, so the solution just harmonic oscillator x of t, right, will be a sine omega t plus phi, and p of t will be a m omega cosine omega t plus delta. And it's easy to see the reason because if you let's say if you dot with x dot double dot, you get m dot divided by m. So it's negative omega x squared, right? So you get x double dot plus omega squared x squared equals to 0. And then you can also see get the same equations like this. Okay, so you get this. Okay, so this is the classical results. Okay, so let's go to the quantum mechanics. Okay, so in other problems that I use the Ermine polynomial to solve these problems. So in this video, we will not do this. We will use the standard quantum mechanics, the algebraic approach. Okay, so let's quickly see. So h now I written as p hat divided by 2m plus m omega x hat, right? So let's do it. Let's written as this. Right, so we just divide it times this h bar omega divided by 2 and do some changes and make this to be this. And this one is basically p hat m h bar omega plus, no, sorry, there's no 2 here. Oh, sorry, this is m. Okay, and this one is just basically m omega x hat square h bar. Okay, so I can that m, let's say this m tilde to be m hat, to be p hat divided by m h bar omega square root, and this q, let's say q tilde will be m omega divided by h bar square root x hat. Okay, so this will, right, so this can be written as h bar omega divided by 2 p tilde square plus q tilde square. Okay, right, so you know that if we do the first quantization, then p hat x hat will be proportional to let's say what is this? So xp is I h bar, right? So this is negative I h bar. So it tells you that this p tilde and the q tilde will be, if you times this, then it will be h bar, right? So then exactly it will be negative I, right? Because the h bar will cancel. Okay, so right, h bar will cancel, right? So we get this. Okay, so we are very quick to get the results. Okay. Okay, so the next thing is that we need to define a standard lowering and raising operators, right? So we start from here. Okay, so the standard is that I define a to be 1 over square root q tilde plus ip tilde, and also a dagger will be square root q tilde minus ip tilde. Okay, so we can solve this q tilde will be 1 over square root a plus a dagger. and the p tilde will be I square root a minus a Dagger minus a. Okay, so just directly solving this 2. Then we can just check a Dagger a will be 1/2, right? So this q tilde minus ip tilde, q tilde plus ip tilde, so it becomes a half q tilde square plus p tilde square, and I q tilde p tilde minus p tilde q tilde. Okay, so this is a half q tilde square plus p tilde square minus a half, right? Because put it into this, right? So this is I. Okay. So from here and here, right? From here and this one, right? This one and this one, and one can get our final result. Basically, h is basically h bar omega half p squared plus p tilde plus q tilde squared is h bar omega a Dagger a plus a half. Okay. So people will define this n to be a Dagger a. Okay, so h bar will be h hat will be h bar omega n plus a half. Right, so this is the standard quantum mechanics results basically here. Okay, so you see the n, right? These n operators commute with this h, right? So that means they can have the simultaneously eigenvalue, simultaneously eigenvector. So hn, so let's define n to be nn, right? Then from here we get this hn will be h bar omega n plus a half, right? So this is the quantum mechanics results that this is our en. So this is the same as you use the Hermite polynomial. Okay, so that's, and also one can obtain the relationship of this n and a. So we can first check that a Dagger is 1. Okay, and so a Dagger will be a Dagger a plus 1, so it's n plus 1. So one can check this NA will be a Dagger AA. So it's a Dagger A. So it's negative. I think it's negative A, right? And also this NA Dagger will be a Dagger A Dagger. So it's a Dagger A Dagger. So it's a Dagger. Okay, so these three are the computation relations of this. Okay, so actually we didn't prove that this n can be greater or equal to 0, right? So we only say that this n, we are not guaranteed that n can be positive. This n can be positive. Suppose we have this, right? But actually it must be positive, and the reason is that this n is a Dagger a, right? So if you do this, then you get a Dagger n squared, right? Which is exactly n, right? So it's basically, it must be greater or equal to 0 by inner product space. Okay, so I think this is the quick summary of how to use the algebraic equations to get our answer. Okay, the next thing is that we will going to prove that okay, so next things we will prove how A and A Dagger account states. So I think this is probably the final section. So how A Dagger account states. Okay, so let's quickly see whether we can get some results. Okay, so A, right? So the what we know is that so the first thing is that we know NA is negative A, right? So that means A account N were proportional to something n minus n minus 1, right? Because yeah, because n is n. Okay, so let's quickly prove it, right? Otherwise that so let's say n act on your a n, that will be a n n right, minus a n, right? So this is n minus 1 a n. Right, so that means a n will proportional to something square root something n minus 1, right? So from here right, we hope to solve C. Okay, and the reason, and also it's simple that that's quickly maybe we can get something. We just take a square, take the conjugate, so we get C squared, and right, by definition this is n, right? So C is just square root of n, right? Because this is n, right? So we get a n equal to square root n minus 1, and you can prove that a n will be n plus 1, n plus 1. Okay, so that's our quick review of the harmonic oscillator. And finally, I will, the final section is that how to use a dagger to get our Hermite polynomial. So if you use the differential equation, then you can still get a wave function. Just its wave function will be some complex coefficient, but the Hermite polynomial times some exponential something, right? So if you can go to see my other videos, there's a clear description of how you can use the differential equation and the basic property of Hermite polynomial to get your phi, right? But this approach, this algebraic approach and the differential equation approach should be the same. So the next question is that how to connect them, right? So how to connect them? Okay, maybe I erase it. So it's very, and we go large. Okay, so this is the final section. That okay, so to connect, let's just do the ground state. So let's do the ground state. Okay, so the key is that I want to use a dagger to construct ground state, the harmonic oscillator. Okay, and this is a standard textbook result. So a act on 0 will be 0, right? Because 0 is a ground state, and I know that a is a square root of, right, q tilde plus p tilde. Right, and I also use in the quantum mechanics that p tilde in this just that d over dq tilde. Okay, so right from our results. Okay, so it's negative pi. Okay, so here I can take q, right? I can take q as a eigenstate, and a become 1 over square root q tilde ip tilde ground state. Right, becomes 0. So the left hand side one will be q tilde, right? Q tilde plus d over dq tilde, right? Act on 0 will be so this q tilde and 0 will matches as the ground state. So it's the phi 0 q tilde. Okay, so this is this is D, right? So this is differential equations look like this. Right, differential equation for this q tilde is a first order differential equation. Okay, and it's very obvious to say the answer will be just Gaussian. Okay. Okay, then this is the right. So this is the same as the harmonic polynomial results because actually 0 for minus 1. And then you can just change q tilde to go back to q or what we use x. And you can see this is the correct eigenvalue. So after you change it back, then you can get our ground states will be this one. Right, this one. And this can be solved. This can be solved by just normalization. So the result will be this. Right? Okay. So this is the answer. Okay. And also, let's also summarize that for this n, then you can just get n, right? Go with this a dagger and 0 and divide by n factorial. And this is proved by what we get before. Basically, you get this n plus 1, n plus 1. So you can start from 0 and keep stacking this a dagger. Okay, and then you finally, and then do the same. And if you use the computational relationship, then you can get this phi and q will be pi 1 over this pi to n factorial. You don't need to care about this coefficient, right? So q minus dq d dq n, right? Because this is a ground state, right? So you just keep using a dagger as the a dagger as the differential equations and act on n is this and change this. Okay, so from here, that you can see this is exactly the. Okay, so let's change it. Then the harmonic polynomial Hn of z has a property that I proved in our videos. It's this Rutherford formula property. This is n. So compare these two, right? Compare these two. Then you can easily get this phi and q will be this one. Okay, so this is the algebraic approach. Coincident, not as the same as the approach that what we get. By the way, this z minus dzn can be viewed as exponential z dn dzn exponential z. Okay, check this is exactly as this. But there will be minus sign, minus 1 to it. I mean, combine all of this will be this. Okay, I think that's enough for today. And let's see. Okay, so let's finally I also want to say the harmonic, the matrix form. Okay, so finally is the matrix form of an AA data. So n is just what, right? So if we expand the n, then we take this, then it will be n, right? So that means this is a diagonal. Okay, so maybe let's do it slowly. So if we want to find the matrix representation of this n, we will do this, right? And the large n, capital N will be n m n. So it's n delta m n, right? So this n has a matrix representation is 0, 1, 2, 3, right? So it's trivial that everything is just all zeros. Okay. How about this a, right? So we know that the a act on the eigenstate of n will be n minus 1. Oh, sorry, will be n minus 1, right? So if you change it, then it will become 0, 1 square 1 0, 0 0 square 2 0 0 0 0 square 3 0 0. And the proof reason is very easy because if you take an m here, then it will become square root n minus 1. So you only, so this is m equals to 0, m equals to 1, m equals to 2, n equals to 0, n equals to 1, n equals to 2. Right, so if n equals to 1, m equals to 0, then become these points, this point, this point. So this is a, right? And a dagger is exactly the same as this, but change this, right? Just flip, so it becomes the square root. So just do the dagger. Okay, and you can also get q and p, right? Just by combination. So I will now write it down. Okay, and next thing should be the evolution and uncertainty principle. But I think this is already enough for these videos because it's probably too long. Okay, so that's it, and I will see you guys. Maybe see you guys in the next quantum mechanics videos. Bye.